machine accept I think the question was Turing machine accepts epsilon. Okay, so most of you have answered true. So most of you have answered false. Something the question was like this, that Turing machine can or cannot accept, and there was a true and false question. Okay, so actually the answer to this question is that this particular problem is undecidable. It means that sometime it can accept and sometime it cannot accept. So you cannot write it in a true or false, 0 or 1 format. Okay, so this particular property of Turing machine, that it can accept epsilon, is undecidable. Okay, so if you have selected true or false, so all your marks will be given to all. So if anybody has selected true or false, don't worry about it. Your marks in this question, marks will be given to all. So I just want to tell about undecidability. Undecidability means that if you seen the undecidable table, I will get back to this concept a little just after a little bit of time. Okay, so undecidable means that you cannot say for sure that what will be the answer. Will the Turing machine can accept epsilon? Will the Turing machine will not accept epsilon? Okay, so if you take a book, take any book and see the chapter of Turing machine, in that particular if you scroll through all the machines and all the questions, you will never find your initial state as a final state. Okay, so that is why that I said that Turing machine do not accept a epsilon, but actually the perfect answer for this was this is undecidable. Okay, so this particular property is undecidable. Okay, so there are some mathematical proofs exist for this particular question, that we cannot directly say it into a true and false class. And there was another question that was asked by a student in the tute. Just this was a question, I think this particular L1, if you take a look at it, this is a raised to power n, b raised to power n. You know that a raised to power n, b raised to power n is not a regular one. It's a context-free language, as well as it is also given that n is not equal to 100 here. Okay, so till n not equal to 100. So this question is divided into two parts: a raised to power n, b raised to power n, where n is less than 100, and a raised to power n, b raised to power n, which is n greater than equal to 100. Okay, so for both of them, context free, the first one becomes a regular part, the second one becomes a context free part. So this particular this particular language is a context free language, but this is not a context free language, because there are two comparison going on. You know about this. Okay, so the first L1 is not context, L1 is context free, L2 is not context free. Okay, now just let me get back to you. Okay, so there are some important theorems that I want to discuss. I will also uh, explain you why exactly is what exactly is given there. So the theorem one is also a very important one. If a language L, so I'm writing a complete statement, sorry for that, and its complement L dash are both recursive or enumerable. Okay, so I again have to revise something, because okay, so just let me write the theorem completely, then I will take a little bit of a revision in the previous one. Then both are recursive. Okay, so then both languages are recursive. Okay, so you will not understand it by just taking a look at it. I will tell you, don't worry about it. Okay, so in the previous lecture, I think we were discussing about recursive enumerable and recursive languages. Okay, so in that particular lecture, I've told you that there are two types of language in a Turing machine. Okay, the Turing machine can accept two types of language. The first one was recursive enumerable languages, and the second one was recursive languages. Okay, so I already told you that Turing machine accept a very vast amount of languages, and there are some languages, suppose because I am talking about Turing machine as an acceptor. I'm not talking about as a transducer, not talking about as adder, subtractor, or anything. I'm just acting the single single purpose of Turing machine is as an acceptor. So I'm talking about it in terms of acceptor. So if a particular language is given to you, if a particular this is a particular language, and this is all the set of all the set of strings that are possible over sigma. From this, I've taken a set of certain set of strings that is called your language, and that I give a particular string to a Turing machine. And if this Turing machine is able to, if the language is in the string, this Turing machine will definitely halt and tell you that yes, this particular string is in the language. But if the particular string is not in the language, this Turing machine will either halt and say no, this is not in the language, or it can also fall into an infinite loop. Okay, so that is the problem with Turing machine in a recursive enumerable language. Okay, so that is why it is divided into two categories. The second category is the same category that now this is again the language and this is your sigma star. When you give a language towards a Turing machine, it will either say yes, this particular language lies, this particular string lies in the language, and if the particular string is not lie in the language, it can directly reply no, this particular string do not lie in the language. Okay, so there is a difference between recursive enumerable language and recursive languages. Okay, so for recursive languages, we have divided this category in such a way when the string is not in the language, if the Turing machine either answer no, or it can fall into an infinite loop. If this happens, then we call this particular class of languages as recursive enumerable languages. But if it is definitely sure that if a particular string is lie in the language or does not lie in the language, if it is it can answer in a definite amount of time, then that particular class of languages is called a recursive language. So for accepting these languages, the Turing machine is also divided into two parts. Okay, so for the recursive part, the recursive languages is accepted by something called a halting Turing machine, and your this recursive enumerable part is only accepted by a Turing machine. It can be halting, it cannot be halting, it may fall into an infinite loop. Okay, so you can say that this particular thing will become this will become your recursive languages, and this will become your recursive enumerable languages, and this recursive enumerable languages will be accepted by a Turing machine. It can be halting, it cannot be halting, but this recursive languages will be always be accepted by a halting Turing machine. Okay, so that now, because the recursive enumerable language is a superset. Okay, so also this is also a very important thing I want to tell, that how we are able to differentiate that recursive language is a subset of a recursive enumerable language. Okay, so this is not in your syllabus, but just for the sake of understanding, I'm telling you that there is a proof, that is you will find the proof if you search it on the net, or you can refer to Peter Lind's book. You will find a proof there. In that book, they said that there is at least, the proof is very difficult to understand, so just take 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 what I'm saying. The proof says that at least one language is present, which is recursive enumerable but not recursive. Okay, so based on this particular theorem, I am able to say that if there is at least one language is present that is recursive enumerable but not recursive, due to this particular statement, I can say that recursive is a subset of recursive enumerable. Okay, so that is the only reason I can say. Okay, so now if you see the whole Chomsky hierarchy, now the recursive and recursive enumerable and Turing machine is also divided into two parts. Okay, so now I'll draw the complete diagram. If you remember that I've started with, I'll now draw the complete diagram. I've started with the finite automata. If you remember, I've started with the finite automata. For this is also referred to as now for this corresponding to this, there is something called a regular grammar. Okay, so this is your type 3 grammar. Okay, so just let me write it like this, and then the acceptor of this is your I think, oh sorry, this is your finite. Okay, so the generator, the language is denoted by your regular language. Okay, so I'm just doing it now differently. Okay, another acceptor was your DPDA and the corresponding language or the corresponding grammar to context free grammar, and here it was deterministic CFL. Okay, so I think I got it wrong here. So here I think it was CFG. More specifically, you can say it is deterministic CFG. Okay, so I can write it like this one. Also write it like this one. Okay, so now after that, there was something called a NPDA, non-deterministic position automata. So now you can write this particular thing. The corresponding to it was your deterministic, non-deterministic CF. You can also call it CFL. Okay, so there is no specific, there is no need to specifically mention an N here. If you remember, I have already told you. So corresponding to it was your context free grammar. Okay, so you can say N is already there. So keep in mind, I will not specifically write a N here. Okay, sorry, I have to write a specific N here. In deterministic part, I do not want to write it. So I just confused. Okay, so now also we have also done linear bounded automata now. So this diagram is a little bit again extended. It will be your LBA here. I think it becomes a little big. Now corresponding to that, there will be a context sensitive language, and corresponding to this will be your context sensitive grammar. Okay, so this is type 3, type 2, type 1. Okay, so this is also type 2 and this is your type 1. Okay, so just okay, so now now it will become your halting Turing machine, and then your final will be your Turing machine. Okay, corresponding to this will be the same grammar. So it is, both of them are corresponding to unrestricted grammar. Okay, unrestricted. I will also tell you about the grammar, don't worry about it. And then for halting Turing machine, the particular language is referred to as recursive language, and for total Turing machine, it is referred to as recursive enumerable language. Okay, so this is now your complete Chomsky hierarchy. This is also referred, this complete diagram is referred to as Chomsky hierarchy. Okay, so it's a little bit not a tidy one. Okay, so you can draw it completely fine. Okay, so keep in mind, everything is a subset or superset of the further languages. Okay, suppose there is a regular language is also recursive enumerable as well as context sensitive as well as DCFL, CFL. Okay, so for this and this and this and this, if a particular language is DCFL, it is NCFL, CSL, recursive enumerable. If a particular language is NCFL, it is CSL, recursive language and enumerable. In the same way, you can go for the acceptor part also. Okay, so this is your acceptors, this is your languages, corresponding languages, and this is your grammar. Okay, so now keep in mind, this whole diagram is referred to as Chomsky hierarchy. Chomsky hierarchy. We also studied Chomsky normal form. Remember, these are two different things. Chomsky hierarchy is designed by this, and Chomsky normal form is a different thing. Okay, so now just let me get back to the statement that I've already told you. Now you know that for a recursive language, there is always a halting Turing machine, that it will stop. It will say that yes, say the particular string is in the language. No, a particular string is not in the language. But for a recursive enumerable language, there exists a particular, at least one language that is recursive enumerable. So I can say that for a recursive enumerable language, it can also fall into an infinite loop. So that is the very big problem that we face. So now that is why it is divided into recursive and recursive enumerable. So the question says that if a language L and its complement, so this is a complement, so I just write it complement L dash. If a language L and its complement L dash are both recursively enumerable, then both languages are recursive. This is a very important theorem. Okay, so you will not understand it. Just let me explain you that what is the meaning of this. Okay, So just take, let me take the statement. So now it says if a language, and its complement L dash are both recursive enumerable, then both languages are recursive. Okay. So now what exactly is the meaning of it? Suppose again I will explain you the same part here. So recursive, I just let me tell you the differences here again. So recursive enumerable and recursive language. So this is your recursive enumerable, and this is your recursive language. Okay. So for recursive enumerable, for a Turing machine, I'm just writing the diagram here. If the particular string is in the language, it will say yes, it is in the language. If it is not in the language, it can say no, or it can either fall into a what do you say, infinite loop. But for a recursive language, when it is you give it to the Turing machine, it will always say yes, it is in the language, particular string is belonging to the language, and a particular string does not belong to the language. Okay, so particular string does not belong to the language. For this part, when a particular string does not belong to the language, it can either say no, or it can either fall into an infinite loop. But if a particular string is in the language, it will definitely tell you, it will halt and tell you that a particular string is in the language. Okay, so only difference between these two are this. Okay, so this is your recursive enumerable, this is your recursive. This particular thing is also called your membership algorithm. Okay, so membership algorithm means you have to find out that a particular string is a member of a particular grammar. Okay, so that is why particular algorithm, membership algorithm does not exist. Okay, so you can say that membership algorithm does not exist for recursive enumerable language, but membership algorithm for this one exists. Okay, so if you're seeing membership algorithm, why it exists? Because it can say that a particular string lies or not lies in the language. Okay, so that is why the membership algorithm exists for recursive languages. The membership algorithm does not exist for recursive enumerable. Now get back to the theorem. Now the theorem is saying, suppose how do I explain this one? So just take a look. Suppose there is a sigma star. Okay, so sigma star, sigma star is a set of all strings that is possible over the input alphabet sigma. Okay, so now this is your language L. So most definitely the language that is not contained in this, it will become your L complement. Okay, so this is your language L, and this is your language L complement. Now look at the statement. It is saying that if a language L or its complement are both recursively enumerable. Okay, so it's saying that L as well as L complement is recursively enumerable. So what it means, that if I take a language L and give it to a Turing machine, it will say if the particular language is in the it's in the if the particular string is in the language, it will say yes. Okay, but but if I give L complement, means that if a particular string is not in the language, if I give this particular string this Turing machine, it can either say no, or it can fall into an infinite loop. But if you see that the statement, look at the statement, is saying L is L and complement of L is recursively enumerable. Okay, so if L dash is recursively enumerable, so one thing I can definitely say, just wait for a second. One thing I can definitely say now, if L dash, now see, L dash is also recursively enumerable. What happened? Just wait for a second. Okay. Now it is also saying that L dash is also recursively enumerable. So if L dash is recursively enumerable, if a language is from L dash, if I give it to a Turing machine, it can also reply yes. Yes, this particular language L dash, this particular string from a L dash is a part of this language, but it cannot reply no. Okay. So by this, if you're seeing this is L and this is L dash, it is one thing it can say definitely, for because L is also recursively enumerable, L dash is also recursively enumerable. So that is, I'm giving you the proofs. Just look at it. L is also recursively enumerable. So it can, if the string is in the language, it can say yes, the string lies in the language. It can halt and stop and say yes, this particular string lies in the language. L dash is also recursively enumerable. So it can halt and say yes, this particular string lies in the language. I am not talking about no, because it can definitely fall into no or a infinite loop. But I am, one thing I'm definitely sure, that it will always halt and say yes if a particular string lies in the language. Okay, so now what can I do? I can make a new Turing machine by combining these two Turing machines. So I can make a new Turing machine by combining a new Turing machine, that name it as Turing machine large. Okay, so now this Turing machine, what I'll do for this, now I'm referring to now I'm changing this language. If string lies, if string lies lies for language L. I'm talking about in the context of L now. Okay, so if a string lies in the language, it will reply to me yes. If a string does not lie in the language, it will lie in the complement. Yeah, if a string does not lie in this L, it will definitely lie in the complement. Okay, so now I can change this yes to a no. Okay, so now this particular, now my Turing machine will always reply, if it's for L, if a particular string lies in L, it will reply to me yes, it lies in L. If my particular string does not lie in L, it will definitely reply that this particular string does not lie in L. So that is why the statement goes like this: if a language L and its complement L are both recursively enumerable, then both languages are referred to as a recursive language. Now your Turing machine that was previously not a halting Turing machine, now it becomes a halting Turing machine. Okay, so that is why it's very important to understand this statement. It's a very important theorem. That is why I also giving you the proof. I'm also giving you the proof that this is how you can prove that if a particular language L and its complement L dash are both recursively enumerable, then both languages are recursive. Okay, so why I'm referring it to as a recursive, because now my Turing machine that was not halting before, that was not halting before on no, now it's if I combine these two different Turing machine into a large Turing machine, it always begin to halt. So if my Turing machine becomes a halting Turing machine, then I can say that my the both recursively enumerable languages are reduced to a recursive language. Okay, so keep in mind, for recursive it is halting Turing machine. For recursively enumerable, it's a simple Turing machine. In Turing machine, this Turing machine can halt, cannot halt. I cannot say anything about it. But for this recursive recursive or halting Turing machine, I can, one thing I can say definitely, then my Turing machine will always halt. Okay, so that is very important to understand. Okay, so there is another confusing theorem that I also want to tell you. It's a very easy, it's a very easy to understand. Okay, so if you don't understand this one, this concept, just let me know. If L is recursive and L dash is also recursive. So these are most this I find that most of the questions in very competitive exams are asked from this proof. So that is why I'm writing this proof, like L dash is also recursive. If L is recursive and L dash is also recursive, consequently and consequently, so just pardon the spelling, both are recursively enumerable. Okay, so it is again little bit confusing statement here, that but it's a very easy one. Okay, so there is no this is just a common sense here. Okay, so now it is saying that if L is recursively and L dash is also recursive. Okay, so it is saying that your L is recursive. It means for this particular string there is a halting Turing machine exists. For this particular string there is also a halting Turing machine. Okay, so it means that this L as well as L dash, L dash as well as L are both recursive. So they can be we can say that they are both recursively enumerable, because if you're saying that every recursively enumerable, every recursive language is also a recursively enumerable language, because recursive is a subset of recursive enumerable. If a language L or L dash is recursive, you can say that L is also a recursively enumerable. So it is just based on a subset theory. If you remember, I've already told you, just refer to this Chomsky hierarchy. If a particular language is recursive, you can also say that language is recursively enumerable also. So that is why this theorem it just seems a little bit confusing, but it just based on this simple property. Okay, so you can also say that uh, you can refer your halting Turing machine. Now, what exactly it means that uh, every Turing machine, this every halting Turing machine can be a Turing machine, but every Turing machine cannot be a halting Turing machine. Okay, so keep this statement is very important. I think you all of you have studied and seen this diagram across all the computer science subjects. I have seen, if you have done DBMS also, you have seen this one NF, then 2NF, then 3NF, this type of diagram. Okay, so you already said that if it is 1NF, it has to be in 2NF, something like this. If it is 1NF, it proceed further for checking 2NF. If it is in 2NF, then you proceed further for checking 3NF, something like these statements. If you considered compiler construction, and in many networking case also, this type of diagram will always be visible to you. Okay, so these two statements are very important. Just keep in mind this is an important concept. Okay, so just keep these statements in mind, and there can be many variants of question that is asked in many competitive exams. Okay, so now your only some last topic is left of your Turing machine that I want to tell you. That last topic is, uh, there are some basics before attempting the topic. There is something called a post correspondence problem. Okay, so before telling about you about the post correspondence problem, I have to tell you about what exactly is undecidability and what exactly is computability and how it is different from undecidability. Okay, so I now want to combine these two concepts. So there is two concepts here. That one concept is computability. You have heard about it most of the time, and then there is another concept as decidability. Okay, so now computability concept is being mostly referred in algorithm study. Okay, so if you have studied algorithms, you will find something, this particular word, as computable. Now, what exactly is the meaning of computable? Suppose there is some function that is given to you, and the function something like it finds the square, or it finds like something like this, fn n square plus 1. Okay, so some function is given to you like this. It has a particular domain. So I will say my domain means that by n, where by the value of n lies. So my domain can be all positive numbers, all positive numbers. Okay, so I'm just all positive number. So on this domain, you put a 1 here, you can get the corresponding value here. You put a 2 here, you get a corresponding value here. Okay, so now what exactly I want to say, suppose now, because you know that what exactly is a halting Turing machine. Okay, so I can say, when I want to say if there is a particular algorithm exist for a particular program or a particular program, it means for a particular problem or a particular program, I just means to say that there is some halting Turing machine exist. Okay, so existing, or if there is an algorithm, it means I want to say that there is some halting Turing machine that will always halt at a particular amount of time. That time is always polynomial. Don't worry about it. That part I will tell you about when I come to P and NP. If there is enough time, I will also relate the concept of P and NP with Turing machine. Okay, so to understand the concept of P and NP from the perspective of Turing machine, it is very easy to understand. Okay, so in both the concept of NP and NP, if you have studied in algorithms, there the terms are used very complex. But if you understand the concept of P and NP from halting Turing machine or Turing machine, you will easily understand from there also. Okay, so I will again relate these two in the end. Just now see uh, what exactly is a computability. Okay, so I can say that given a particular function and a particular domain, if there is a Turing machine which will produce a output on the tape for every input, then I can say that such function is termed as computable. Okay, so if you don't understand it, I will say want to say if there is a Turing machine, if there is a Turing machine which will produce some output, which will produce Turing machine means halting Turing machine. I'm talking about halting Turing machine. If there is a Turing machine which will produce the output on a tape for every input, the input should be from the domain. Keep in mind the input should be from the domain. And I'm talking about only I'm only talking about uh, halting Turing machine. Keep in mind I'm only talking about halting Turing machine. Okay, so in terms of algorithm, if you are able to design a halting Turing machine which will produce the output on the tape based on the input that is for all positive numbers, so it is this function, this particular function will be called a computable function. Okay, so you put the value, you are obtain the corresponding result, you put the value, you obtain the corresponding result. So this thing is particularly referred to as a computable problem or computability of a particular function or anything, but the decidability is somewhat different. Okay, so I am only interested in a problem, not a function. First, I'm not interested in a function, I'm interested in a problem, more specifically the answer of true or false. Okay, so if I'm able to reduce the problem through a true and false question, that either you can say that it is true or a false, then I can say that a particular problem is decidable. If you are not able to answer this thing that either it is true or false, then a particular thing will become undecidable problem. Okay, suppose this example can be is n a prime number, is n a prime. Okay, so I have to set the domain also, so domain can be set of all natural numbers, natural. Okay, so I can say that if there is an algo, if there is an algo exist, if there is an algorithm, algo means that halting Turing machine, if there is an algorithm exist, then you can directly say then it is a decidable problem. There is no need to check anything, you can directly say. So algorithm is just here it is also referring to as a halting Turing machine. If a particular, for a particular problem, what exactly halting Turing machine say, that if the halting Turing machine will stop, it will say yes, the particular number is prime, or if it is if or it can say no, the particular number is not prime. Okay, so keep in mind that decidability and undecidability is a little bit it is a little bit complex thing to understand. First of all, this is, I again want to contribute to one statement. For a single instant, every problem is decidable. Okay, so I again want to say for a single instance, every problem is decidable. Take any undecidable problem, take a single instance of it. For a single instant, any problem is decidable. I'll give you example. Okay, so now we know that there is a very popular problem that is referred to as uh, a grammar is ambiguous, is G is ambiguous. Okay, so this is a very popular undecidable problem. I cannot develop an algorithm. I also told you that for finding a particular grammar, if a particular grammar is ambiguous or not, you are not, there is no such procedure exist. You have to go by hit and trial method. I've already told you in the lecture. So there is no algorithm exist for it. This is a popular undecidable problem that I cannot decide this one. But if I reduce the domain, okay, so now that domain, for now I just delete this particular thing. Now I'll say the domain is grammar G1 for a particular grammar. Okay, so for a particular grammar I can say that thus this is decidable. But if I increase the domain, okay, so if I increase the domain to something like all the CFG grammars of the context free grammars, all the context free grammars. Okay, so now the domain becomes large. So again, this problem is classic undecidable problem. You cannot say for all the grammars, you cannot develop a particular algorithm for all context-free grammar that you give input a context-free grammar, and it can say for by following a particular algorithm, it can say that a particular grammar is yes, it is ambiguous, or no, it's not ambiguous. Okay, so that is the main concern. So this is also a very important problem, that for a single instant, for a single instance, any problem is decidable. So actually, this is a very this is a classic undecidable problem. But for a single instance, we are seeing only I'm asking for a G1. For a G1, you can already always design an algorithm. For a single problem, you can always design an algorithm. But for if I increase the domain, this again becomes an undecidable problem. Okay. 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 So I think that is enough for now. So there is only two statement left, and I will again, there is again very interesting problem of Turing machine halting problem. Okay. So this is also very interesting. And in the end, I will finish it with the post correspondence problem and your P and NP. I will tell you a little bit about P and NP. It is very easy to, if you understand this particular, I know it's very confusing. Turing machine is very confusing concept, but if you take a look at it, because most of the things are still not proved, so that is why it's a very confusing concept. But